So we're going to go ahead and get started again. This session here is really a session that'll be devoted to us giving you some insight on what kind of resources are available for you to do work. In labs like mine, CNS, Center for Nanoscale Systems, which is part of the National Nanotechnology Infrastructure, the DOE labs, where Kenneth, who's at Brookhaven, you just heard from Sean, who's the director at Argonne, and also William Radcliffe is going to talk about some of the resources available at NIST. And we'll kind of go through that pretty quickly, and then I think we'll just open it to questions. The one thing I will tell you is don't get overly concerned with kind of snapping pictures and stuff, because my plan is to aggregate all of this stuff and put it on the website as an ensemble of links when the meeting is over. So, and you can harass me if I don't do that quickly enough. So I'm going to start off with kind of a description of the Center for Nanoscale Systems, a brief description. You guys already saw CNS because you had your poster session there yesterday. I know there were some tours, but I'm always somewhat annoyed sometimes when my staff gives tours because each group of staff only shows half the lab. So if you got a tour from a guy who's on the fab side, he only showed you the fab stuff. And if you got a tour from the guys on the electron microscopy and imaging side, they probably only showed you the imaging stuff. But I'll tell you that we're basically a one-stop shop for all things nano and quantum. Bob Westervelt's been here the entire week. He's one of my biggest cheerleaders. And our primary responsibility is to create an environment where somebody can do prize-winning work in our building. And that's our focus. Okay, we are an open facility. Nearly half of our user base is non-Harvard. We're also a pretty substantial both regional and national facility. Okay, so what we're cultivating here really is one of the most comprehensive nanotechnology, quantum technology research facilities really in the world, right? We have two primary cores, nanofabrication core, which is component driven, a pretty wide variety of tool sets. Our wheelhouse is non-traditional materials. And so when you see these strange devices in lithium niobate and 2D materials, all of that processing and development is done and taught here. And we try to make kind of multiple length scales available, from being able to do e-beam lithography of small quantum dot devices that are 5, 10 nanometers in diameter, all the way up to being able to 3D print something, right? On the imaging side, and for the most part, if you talk to any of the startups locally, they will tell you we're an advanced prototyping shop, right? We make widgets. Okay, on the electron microscopy and analysis side, we do a pretty wide variety of advanced imaging, particularly atomic resolution electron microscopy. And some of those tools I think folks showed a little bit yesterday. We have quite a bit of analytical instrumentation. We do a ton of cryo electron microscopy. We do a lot of biology, more biology than you would think. We do some atom probe tomography. And then our lab, as you saw, we're at the basement. We actually occupy the bottom 2 floors of the leased building, where you were at yesterday. And when you guys, after dinner, you had some wine tonight, asking me why the basement you were in yesterday was called the ground floor. I'll tell you the story. We have and you saw we have a 10,000 square foot clean room. We have 6,000 square feet of high resolution electron microscopy suites. We have a cell culture lab. We do a ton of soft lithography. We have a soft lithography, a biomaterial space. We have an optical spectroscopy lab. And then we also have a scan probe microscopy laboratory. We also have new facilities for what's kind of evolving more for bioengineering, kind of soft matter, in our new engineering building over by the Biz School. We now have 2 SEMs over there now. We have 1 new TEM over there now. Again, we have a soft lithography lab, which I think I'm going to repurpose for something else because everybody comes over here to do their soft lithography. And it's because nobody wants to relearn their process, right? Nobody wants to redevelop it. And so one of the things we're in the mode now of sorting out is how do we allocate resources for that? So we have rheometers and a bunch of other soft matter tools over there in those labs. And we've added a few staff to support that. And for us, the work product is the science. I joke all the time when I have my annual meeting with the deans, I negotiate with them how much money we're allowed to lose, right? We don't make any money. Our job is to allow people to do excellent science. You can actually take a tour of the lab. One of the things we did during the pandemic is we built a virtual model of the lab. You can actually go to this model and take a walking tour. In fact, it made the Cambridge Police Department really nervous when I told them we had done this. And you see the blue pucks on the images there. If you go to the map and you click on a blue puck, it'll take you to an instrument. Each individual instrument also has kind of a link to it. If you click on the link on that instrument, it'll take you to the web page so you can sign up and get access. It'll tell you everything you need to get trained, everything you need to have as prerequisites before you do the work, and we'll marshal you through the process. And I'll give you a few lab stats. Right, our user base, right now we're up to about 1,500. Typically, we do 1,500 to 1,800 users a year, and every year we restart that count because we make everybody re-register. We have 33 staff, easily every year, about 150,000 hours of work in the labs. And as I mentioned earlier, on average, half of our user base is non-Harvard. About 20% of my user base is from MIT. Okay. And of course, in all sectors are represented in that. In fact, I think right now, we're up to maybe total 18 or 19% small companies that kind of bounce up and down. We have a ton of startups. And then, of course, every kind of science you can imagine is done in our building. A ton of work in traditional physics, material science, optics, and photonics. More recently, a lot of life science work. The life science folks are doing simpler things, but the number of them is actually getting to be pretty big. If you actually rescale this, instead of by number of users, by hours, the traditional guys would have bigger pieces of the pie, but we're getting lots and lots of interaction with folks from the medical school and bioengineering and biophysics in general. All walking through kind of taking advantages of using these tools to do their science. We do have a core research focus. Our core research focus here, driven by the local researchers here, really is kind of quantum science and engineering. And in that, a quantum information science and devices, I would say a lot of nano-optics, a lot of nanophotonics, a lot of integrated photonics, which actually isn't on this list. But we do have folks doing, quantitative biology, whether they're looking at nanomechanics or doing structural analysis. And we have a ton of people doing translational bioscience. Right? And actually, one of the things that was interesting is that a lot of the infrastructure here, in terms of the kinds of stuff we do, was built off of the work that was done in CEQUM, the Center for Integrated Quantum Materials. And so over the years, we've kind of morphed ourselves into being the infrastructure arm for CEQUM-type projects. And so we've come naturally to all of this quantum device work. Okay, I think this is mentioned in passing. We do actually have some relationships with companies. We have a quantum networking alliance with the folks at Amazon. I would say people want to learn a little bit more about that. They should poke me offline. Over the last couple years, we've been becoming more and more ingrained in the teaching mission at Harvard. We're now teaching classes in our labs. On the fab side, those classes are pretty modest in size, but people are really enthusiastic about them and they love them. And in fact, they poke us all the time that we should teach more. I'm not sure we have the bandwidth to teach more, but But it's definitely a tremendous amount of interest in that. And then, of course, we also support classes in other departments. Arthur, for example, has been effectively a teaching fellow for Chem 165 for 10 years. So that's the Advanced Experimental Laboratory in the Chemistry Department. And they do a lot of their projects in our labs. And of course, we teach a ton of electron microscopy courses. But the main thing I want to mention is that we are the New England hub for the National Nanotechnology Infrastructure. We're over, of course, on that course over there. There's 16 sites, kind of a little over $81 million of funding. We're kind of almost 10 years in, right? Yeah, because I think we've done 2 cycles of this. The money we get from the National Science Foundation, we use it exclusively for outreach. And so we have a pretty wide variety of initiatives supported here through NNCI. As I mentioned earlier, we have a research experience for veterans program, which I thought was a great way of turning veterans into clean room engineers, but it turns out they go to graduate school like everybody else. But we also have, a conventional REU program. We actually helped kind of seed the establishment of a National Society of Black Physicists chapter here at Harvard, and now there's a sister chapter at MIT. Actually, you guys have seen Greg Cunningham and Nicole running around here, and most of our ambassadors from MIT and from Harvard that you've seen during this event are folks that are in NSBP. But what might be more interesting to a lot of you is that we have a program that we run called CNS Scholars. And what CNS Scholars is a program where we try to get you collaboratively coupled with folks doing work in the space that you're interested in here. And then we'll also support your usage. And so we've had a number of folks, a few people in the room who've actually been CNS Scholars over the years. I always say that our best graduate at this point is Chris Dorsey, who was at Smith College. She used her CNS Scholars support to get an NSF Career Award and then got poached by Northeastern. And so she's now a tenured professor at Northeastern, but she still collaborates with Rob Wood and the folks in soft robotics who she met when she was interacting at CNS. We have a ton of interactions with startups. Actually, the folks who were here earlier from Atlantic Quantum actually started at the Engine. The Engine is actually a venture firm. It's actually kind of a weird venture firm. It's kind of a technology incubator that also funds some of the companies in the incubator. But also Marco Loncar's company, Hyperlight, that does high-speed modulators, is also an Engine company. But we've been doing a lot of interactions with those folks over the years. It actually was kind of a cheap ploy by me. I was always worried about small companies disappearing before they actually paid us. Right. And so I said, well, if I get the incubators to support us and fund them through the incubators, I can charge the incubators if the company disappears. Right. And we did that specifically originally with Greentown Labs, which is a incubator that's locally in Somerville that hosts a pretty wide variety of green energy companies. And it's actually worked spectacularly well. Right. And it turns out there are students anyway. I mean, most of the students who are starting these startups are folks who are here as graduate students. Right. And so we've already seen them. We have a couple small companies that have gotten us into a regime where it's getting kind of weird. Hyperlight and Metalens are the best examples. At some point, we have to stop calling them small. I mean, Metalens started out, their corporate headquarters was our cafe in the lease building. I think they now have their own building. And so I tell Rob Devlin all the time, and I mentioned this to Federico Capasso, at some point they owe us an endowment. And so I'm going to mention, quit on the programs for CNS, and I want to mention there are programs at some of the other facilities. Okay, so this is the RTNN. This is the Research Triangle Nanotechnology Network. It's really NC State, Duke, North Carolina, Chapel Hill are the primary drivers in that. I think North Carolina Greenville is also part of this consortium. But the key thing here is they have a bunch of interesting programs if people just want to go in and just kind of play around. They have a program called Kickstarter, where if you have kind of a weird idea that you think you can do there, they'll give you $1,000 worth of usage time and you can roll in and you can try your crazy idea. But they also have nanotechnology and processing courses online. Actually, Stanford is doing the same thing too. A bunch of educational outreach programs. So there are a lot of opportunities available throughout the entire NNCI. Yeah, for folks who are interested kind of in sustainability, they're the folks at NanoEarth. NanoEarth is out of Virginia. I think the main lead institution is Virginia Tech, right? And they're really kind of focused on sustainability activities. But again, they have seed money, opportunities, and access to do all kinds of a pretty wide variety of experimental techniques. But they're also more than helpful in pulling you into this science if you want to get into the sustainability space. And then the last place I will mention here is I wanted to mention the Singh Center at Penn. And so this is Manth. And what's interesting about the center at Penn is that Penn has already started developing programs with Community College of Philadelphia to give technicians degrees, and they do micro internships there. And especially for you, Idris, these are the folks that you kind of need to poke for some of the programs that you're running in the city. Okay, but the main thing is that there are a pretty wide variety of these programs all over the NNCI, and they're programs that range from K to 12 all the way past junior college to graduate school and a few postdoctoral programs. But the goal is all of us are kind of serving this continuum of workforce, right? And so, like I said, I will put all of this information on the website, and so you'll get a sense of make sure you know who to poke at any institution to find out what's really available to you. And so I'm going to hand it over to Ken.
All right. So first off, raise your hand if you've ever heard of NIST. All right, a surprisingly large fraction of the room. So NIST, we primarily have two campuses, one in Gaithersburg, Maryland, about an hour from DC, center of the universe. We get a lot of people who come out to visit NSF or DOE to get money, and when they come by, they'll also stop by and visit us. In particular, I'm at the NIST Center for Neutron Research, where we run a user program when we're operational. Where people can come in and use our nuclear reactor to do experiments. Where when we're running, we run for 38 days, down for, say 11 days, up for 38, down for 11, and people do a variety of science. So I thought I'd try to give you just a flavor of some of what we have going on at NIST that's relevant for this program without going into any detail. So some of this is research that's being done in my division at NCNR, but I've tried to cover things that are going on beyond the NCNR and beyond my own expertise, which is on quantum materials. And then here I'm just showing off some of our instruments where we can do things like measure structure and dynamics of materials like superconductors. We can do in situ measurements of things like batteries. For those of you that are interested in polymers, we can look at low resolution structures and map out phase diagrams of those. And so we have some pretty versatile tools over at the reactor. And I'll show you a couple of projects that were going on. This is one done by some of my coworkers where they're looking at some of these flat band materials. So you heard the graphene talk earlier, but you can do flat bands outside of graphene. You can do them in solid state materials. These are on what's called a Kagome lattice. So it's a solid state lattice. And the where you have a network of corner sharing triangles, and this gives rise to flat bands where you can get various topological effects. And so with neutron scattering, we can study not just the structure of these materials, but because the neutrons have a magnetic moment, we can look at magnetic ordering in the materials and then see how the magnetic order goes and gives rise to changes in the band structure, which then allows for things like topological Hall effects. And so these are just some cartoons of this where you can go and see, a bit of the structure, a little bit of transport and magnetization, but then also the mapping out of this phase diagram where neutron scattering played a critical role in this in determining various changes in the magnetic structure as a function of field, which then fed into various theoretical models where examinations of the fluctuations gave rise to the topological Hall effect in these materials. And people care about this, sort of generally these classes of materials for what's called fault-tolerant quantum computing, which we sort of leap into in the next one, where we also have a probe called reflectometry, where we can measure magnetization as a function of layer thickness. We can also measure hydrogen as a function of layer thickness, which comes in later. But in this case, the idea is that you have a topological insulator. You then have an interface with another material, in this case, iron telluride, for those in the know, a little controversial. But the idea is that if you put the topological insulator in close proximity to a material that it may be topological superconductor, that you can actually induce the topological superconductivity there. And if you have a topological superconductor, you care about this because the excitations in these materials are what are called Majorana's. And then the Majorana's, you can quote unquote braid them, and then that will give rise to fault tolerant states. So that if you end up having disorder, you don't have to deal with all of the error correction that we've heard discussed at length later. Companies like Microsoft are interested in this approach, and we can talk offline with some of the various materials challenges and such that have been associated with that. And then since we're and this is just a little bit more of that. There was also a nice study that my coworker did in collaboration with Julia Mundy and several other groups. So Julia Mundy is a researcher here that some of you might have seen at your poster session, where there was a new superconductor that was discovered, and there's been lots of questions about the role of hydrogen in the properties, and neutrons have been very uniquely positioned to measure that. And again, I'm just trying to give you a flavor of some of what we do. So here's an example of another topological superconductor that we measured, but now I'll give a shout out to another lab. This is mainly done with measurements at the National High Magnetic Field Labs by my colleague, Nick Butch. And again, the interest in this compound, which is a little bit of an accident in terms of discovery, where, his postdoc measured something by, made a material kind of by mistake, but it turned out to be incredibly interesting because it may be the only known example of a triplet superconductor. People had hopes and dreams of strontium-2 ruthenium-04. Unfortunately, those were dashed against the rocks due to long-term measurement errors, but that's another story we can discuss later. Oops, I think I'm being recorded, but okay, everyone knows. This is like a very good example, though, of this triplet superconductor, where again the excitations are interesting for the possibilities of being able to do fault-tolerant quantum computing as compared to the more traditional qubits that are made, like with niobium or, as we learned, tantalum. Some of my colleagues in other divisions are involved with synthesis. I think they were wanting to call this some sort of foundry where there's attempts on this, but generally we can create and measure a wide swath of 2D van der Waals materials, and these have been quite interesting in terms of the topology of the band structure, which you've heard about earlier in terms of things like anomalous quantum Hall effects and such. And again, very, very interesting from transport and devices. But this is sort of basic physics measurements on these, where we've done some cases, we've done bulk measurements, like say in molybdenum-telluride, and found hints that may hints of topological superconductivity. There's manganese bismuth 2 tellurium-4, where there are analogs of that, where this is like an intrinsic topological material, et cetera, et cetera. And we're working on trying to build up capacity to do even film growth of actinides. So like imagine you want to grow a thin film, but you want to grow it with uranium. There aren't so many places, maybe one place else in the world where you can do that. And so we're trying to stand up that capability. And for anyone who's ever been at a national lab, my colleagues have told me that the safety reviews are somewhat arduous. But again, these are capabilities that we have. And then for those of you that are theorists, one of my other colleagues, Kamal Chowdhury, has been working on building a very detailed database called Jarvis of DFT calculations for these 2D van der Waals materials, which then some of you may use to go forth and make new materials, new devices. And again, that's a facility that's freely available for anyone to use. So just some examples of some calculations from the database. But NIST is very broad, right? And so besides defining the kilogram and, the hardening message earlier about, like our time standards and resistance standards, we're also responsible for the encryption standards of the nation, right? So any of you do online banking, well, the security behind that's produced by NIST in consultation with the NSA. And so already people at NIST are beginning to think about post-quantum encryption and cryptography, and opening a series of competitions to develop different algorithms, so that if anybody here manages to get a working quantum computer, we'll be ready with the next generation of codes, so that we can still keep information safe. And so we have this cryptography group that's very involved in that. Let's see. So here's an area that I know probably the least about, but we actually have a very strong effort in quantum networking. So if that's your passion, then get in touch, and I can put you in touch with our quantum networking group. This is one of the major. This was actually a major thrust of the quantum efforts at NIST, and you've seen this around the country. I mean, like Harvard is very proud of the, of their network at Boston. Since we have someone from Argonne here, I believe that there is a little wire going over to Fermilab. Oh, okay, and Chicago, right? I have to be careful. Wait, where did Nadia go? But yeah, so they have so we there's a lot of efforts on quantum networking. I mean, the VC said, okay, he doesn't know why anybody would want this, like maybe a bank or somebody, I don't know, but nobody important. But this is another set of efforts. I didn't get a slide on this. But before I go into this one, I'll just mention that there's also a strong quantum sensing effort going on at NIST for those who are interested in that. So hopefully they can get me a slide, and when these go online, then that will be available for you as well. I was talking with somebody who does have some involvement with that, though, and there have been some spin-offs more related to our Boulder campus where people are using quantum sensors for oil and gas sensing, as some people have mentioned. And then there's also been mentioning, there was also some nice, there was a really nice talk this morning, about Oak Ridge and how they're using NV centers for imaging and magnetic field detection, et cetera. But that's also is a real biggie because people are also using that to try to do brain imaging. So, already you're seeing people beginning to try to realize quantum sensors for commercial applications. This one is run by a woman over in the Boulder campus, where she actually co-founded this program where they do something for where they try to get women more involved in the quantum space. And so, sort of while we are here, they're actually running a pretty large workshop with an astounding cast of characters, also with some applications of quantum AI, et cetera. So, for those that are interested in like their future workshops, then you can search this out. And again, so Bill said that he was going to talk about opportunities at NIST. So we have a program called SURF, which is our equivalent of an REU for the undergrads in the room. And again, if these will be on the resource page, don't bother, trying to, jot this all down. But, we have our equivalent of an REU. I actually have a student from Boston College this summer who, but, a number of us take on students through there. The reactor, we have another program called CORE, where it's a little bit more tailored. Again, it's basically like an REU program, but it can continue during the semester and we pay. We also take on students from our PRIM partners, so shout out to PRIM, along with like other institutions. So that allows us to have a close partnership with collaborators. It's a little bit more selective. And then, of course, we have an NRC program. Now, our challenge is that the NRC is only open to U.S. citizens, but I'll just pitch it a little bit with the idea that when we bring on our postdocs in general, if they come in through this program, it's very competitive, where they're actually effectively reviewed by the National Academies of Science. You pitch a research proposal saying, all right, this is what you want to work on for the next couple of years of your life. But you have a lot of freedom in terms of doing your own research as compared to, sort of a typical university postdoc, where it's like, all right, you've been brought in to do project X and you will be working on X. And well, you want to do Y, maybe, if you have some free time, like some extra 100% of your 100%, right? So keep that in mind, is that national labs do provide these postdoctoral opportunities. They pay significantly better than most universities can offer. And, like, you also have a fair amount of research freedom, which is good. I'm mentioning the one at NIST because I'm from NIST, but all the labs have their equivalent, so like Argonne has their Metropolis, there's the Oppenheimer at Oak Ridge. I don't remember the one at Brookhaven, but I'm sure that Ken will call it out. But just keep that in mind as you're applying. If you're a U.S. citizen, we'd love to have you. But if you're not, the Department of Energy labs, those normally don't come with citizenship requirements. And so, like that's another possibility. And I guess we'll probably do questions at the end, but if you have questions about NIST, just find me. I'm here through most of the day tomorrow as well. And even if I don't know exactly what's going on for, say, for example, quantum networking, I'm happy to try to connect you.
So my task was a little big. It's DOE Labs, and I'll try to show you how big it is. And so I figured what I'd do is just give you tools to get more information for yourself, is what my plan was. And so next. So briefly about myself. So beamline scientist at NSLS 2. If you want more information on me, you can look up that link there. PhD in condensed matter, 15 years at Bell Labs, and then I've been at Brookhaven. My interests are sort of ongoing ones are studies from surfaces, in situ studies of growth, microdiffraction, all X-rays. And my current interests are studying graphene flakes and other 2D materials, a collaboration I have with Tina Brow-Thomas from Howard. So what I'm here to do, and I mentioned that stuff about myself to simply say I'm not a professional, I'm more from the bench side of the lab. I'm not a HR person telling you about everything in the lab. So this is it from my point of view. So a quick overview of the DOE lab, DOE national labs. There are 17 of them. And what you'll see is that there are some blue and some green. The green ones are nuclear materials, the energy, nuclear weapons labs, basically. And there's Los Alamos, that you'll remember Los Alamos from the Oppenheimer movie. And the blue ones are sort of basic energy sciences, which is where most of us live. What national labs tend to do is they try to have expensive scientific infrastructure for users, equipment that's usually too difficult or too expensive to have in an academic lab. That's kind of where they aim most of their effort. And very often the infrastructure is wrapped up in what's called a user facility, which is actually open for most of you. You just have to write a proposal, find which place has the tools you might be interested in, write a proposal, and you can use these tools. It really lowers the barriers to entry. You can conceive of projects which are way beyond what you have in your local university. Now, of course, a rich university like Harvard University has all the tools it needs, but other places don't. So some of those tools are things like photon sources, advanced electron microscopes, colliders. And so what I'm going to do is show you a few of those infrastructure things. And then keep in mind that even within any of these labs, there are many individuals working on different projects which are more related to your quantum materials, QIS in general. So let's start with Argonne National Labs. And with Argonne, you've got, it's got the advanced photon source, which is a high energy photon energy ring. You've got a nanocenter. And so I don't know if it's obvious, but the ring-like structure at the very top there, that's the APS. It's about 1 kilometer across. It's a $1 billion machine. You've got Oak Ridge National Labs. So that was an X-ray machine. At Oak Ridge National Labs, what they have is a neutron source, this SNS, spallation neutron source. And they also have a nanocenter. The nanocenters are similar to what CNS is over here. They have the high performance computing. And one of their quantum collaborations is called QSC. Lawrence Berkeley has also a photon source, but that photon source is more at the lower, softer photon energies. And it's also got its own nanocenter, the Molecular Foundry. I'll skip Pacific Northwest, but you can see there are many different labs and each one has something different. So for Brookhaven, so this is my home lab, Brookhaven, and this gives you a sense. I just gave you the labs. Now let's look a little bit. So at BNL, we have 4 big facilities that are listed here. RIC, which is an electron-ion collider. It's I think it's like 30 GeV ring. You've got the second item, the CFN. Number 2, that's like the CNS, the nanocenter. And then on number 3 over there is NSLS2, which is where I work. And I think basically DOE has figured out that nanocenters and light sources work pretty well together. There's a lot of synergy between them. You can use the photon sources to study materials. You can use the nanocenters to create stuff for the synchrotron. So there's a lot of synergy there. So one of the things I thought that I wanted to mention was if you're thinking about national labs for a career, first of all, when I was a grad student here in this environment, I had no idea about the vast array of opportunities in the national labs. There are many thousands of scientists working in the national labs. And once you have these large scientific infrastructures, you end up needing more management than you would have at a place like a university. And this is one of the cultural differences between the two kinds between academia and a place like the national labs. And this gives you a wide diversity of career paths. You can lean more towards the scientific path, or you can lean towards the management path at different times in your career. It gives you a little bit more range. And even if you're working in the scientific track, one of the differences is that the resources and the stability of funding over time allows you to address larger scale complex problems. So if it happens that your interests align with projects that are that the lab has a priority, has given a priority to, it can be quite beneficial for your career. An example would be, I think, the DNA sequencing project. That was a big project where the scientists' interest and the lab's interest aligned, and they did a massive thing, which would have been difficult to do in a university environment because of the stability of time. So, and I wanted to make a point. When I was going through, I pointed out how there were different photon rings at the facilities, but the energy, I kept making the point, low energy, high energy. And the thing I want to point out is, even though if you looked at some of those labs, you would say, well, they've got a photon source, they've got a nanocenter. What's the difference between these two labs? The fact is, each facility is slightly different. They optimize each sub-facility slightly differently. And so that has a consequence on the kind of science that will be better suited to one lab or the other. So again, you should look at the kind of science you want to do and look in detail at which lab would better match what you want to do. So that's if you think now. So that was more like for the graduate students and the young faculty. Now, for the undergrads and grads, well, luckily from Sean, you've heard some of this already. Basically, one has a pipeline, one has to try to address all aspects of the pipeline. And so there are university and college programs. You've heard about the SULI program. And so, that's, again, across all the DOE labs. I won't say too much about it, but just a summary, 10 weeks, it's paid for. They even pay you to go there, which is kind of nice. And but they do, at least at BNL, they have you on a track. There are deliverables that are supposed to get done. Now, what Sean didn't talk about much, he kind of mentioned it but went over, is the VFP program. So this is for faculty visit. So in our case, we have, again, Tina Brower Thomas, who has been a VFP member for a couple of years now. And so it's like a summer student for faculty. So that's another resource to take advantage of. And I think the key thing is, I do often get people to call, and because they know me, they think it makes a difference. And the answer is, for DOE lab, there's basically, there's like one way in. You go to the website and you apply. And you have to apply on time, otherwise, like knowing me, I can't go in to anybody and say, could you please open up this particular thing? You got to apply on time, and that's the only way. And so there are places that's where to do it, bnl.gov, and I think, yeah. And then the last thing I'll put on there is this is the end. This is at Long Island at the end, Montauk Point. So anyway, I'll leave it at that point.
Yeah, I will just mention that at NIST, all of the instrument scientists, we're all really happy if somebody comes in. If you haven't done a neutron scattering experiment before, you're just trying to see what's possible. Most of us will happily have discussions with you about the science that you're trying to do, and then take a look at the proposal as you've written it, help you with it as well. So, because we want people to be successful. These are large investments, by the nation. And so, while some of them are toys that we use, they're there for everyone. So, don't feel intimidated if it's something that you haven't done before. Not just NIST, I'll talk about scattering, but not just NIST, but also the DOE labs. We all run summer schools to help people get onboarded. For example, I'll be lecturing at a DOE summer school later this summer. There's a neutron X-ray school where they try to bring people up to speed on how to do neutron and X-ray scattering experiments. Part of the time it's at Oak Ridge, part of the time it's this year at Argonne. And so I'll be going down to give some lectures on single crystal crystallography. But, there are many summer schools, not just on neutron scattering, which happens to be my area, and we run one at NIST, and there's the joint X-ray school, et cetera. But you'll find schools across other disciplines as well, right? So, for example, if you're interested in doing crystal or film growth, I believe that there's a school that Paradigm runs. You can find various DFT schools. There used to be a series of schools just in general, say, for example, on magnetism. I would be shocked if there's not a quantum one somewhere. So just, keep your eyes out, because they're a great way to come up to speed on new and upcoming fields, or even for fields that have been around for a while, but maybe there just isn't expertise at your local university or even in your local group. And even if there is, maybe, they're still wonderful to go to, because, it's a time where you can just focus on learning something for usually about a week, longest a month.